Hi, so for today we're going to talk about equilibrium of a particle, coplanar force system, in statics of rigid bodies. But before that, bati muna tayo, no? So shout out muna tayo. So shout out kay Troy Aldobe from Tayabas, Quezon. Um, Shout out din kay Alex Marcelo from Nueva Ecija University of Science and Technology or NEUST, a civil engineering student. So hi sa'yo. Enjoy sa panonood. Kay Miss Laura Jane Hernandez or LJ Hernandez from NEUST rin, a civil engineering student din. And lastly kay Mariel Jonella, a student of mine in FEU Institute of Technology, also a civil engineering. So, hi sa inyo. Enjoy sa panonood. So, we shall be talking about equilibrium of a particle, coplanar force system. So, this is a very basic, fundamental topic in statics of rigid bodies. But before that, we need first, in studying equilibrium of a particle, uh, there is a condition that the summation of forces along that particle should be equal to zero. Okay? We know that the force is vector. So in 2D, we can have a force projected along the x, along y, or even the combination of forces along x and y. And we know how to express a vector force, okay, in terms of x and in terms of y. So the summation, furthermore, the summation of forces along x and along y should be equal to zero. Okay, in order for us to say that the uh, that particle is in equilibrium. So for today's video, we're going to solve some problems, three problems, basic problems involving the equilibrium of a particle. So for number one, here's the figure. Okay, so determine the tension in cables BA. This is labeled as B, point B and point A. The tension in cable BA and BC, okay, here's our B and C, to support the 60 kilogram cylinder. So as we all know, the cylinder has a mass of 60 kilogram. Okay, so the very first thing, okay, we are going to do in solving these types of problems is we know how to draw the free body diagram of a system. Okay, so to draw first the free body diagram. So if we are going to draw the FBD, okay, or the free body diagram of this, okay, centered at B. So let's say that is our B, point B. Okay, this is our B, point B. So the forces acting, okay, if we are going to center it by B, so we have a weight, okay, due to the mass of the cylinder going downward along Y, purely along Y. And then we have the tensions, BC. Tension, it means it is a pull, okay? Pulling from this point, the tension in this point. So this is, let's label this as tension BC. Okay, and another one here, we have a tension or tension AB. Label it as AB. And then we have given angle, okay, with respect to positive x-axis. So we have 45 degrees. And then we are given a triangle here, okay? Values of triangle, we have 3, 4, and its hypotenuse is 5. Okay, again, we should meet, okay, the uh, condition for equilibrium, which is the summation of forces should equal zero. And we all know that this is a vector or force tension that is not purely along x and y. Hence, we are going to get the components of tension BC and tension AB in terms of its x and y. So, we are going to get the summation of forces first along x. and that should equal to 0. So our convention is that if it is going to the right, we labeled it as positive. Okay? And summation of Fy, okay, if it's going upward, we label it as positive. It doesn't matter what your convention is, but we are used to, if that is going to the right, that's positive. If that's going upward, then it's positive. Then opposite sign for the reverse directions. So, for summation of forces along x, let's write it all. Summation of forces along x, okay? So, should equal to 0. So, we are going to write the summation of forces in x-axis. So let us first start with the TBC, the tension in BC or tension C. Okay, we have TBC. Okay, we are going to get the component of the x component, so that must be cosine 45 degrees minus, if we are going to project this tension AB to the x-axis, it is pointing on to the left. Okay, to the left. So that means that is a minus. Okay, and since if we are going to get the x component of this, we are using cosine. So if we have an angle here, okay, theta, let's say, if we get the cosine of that, since there is a given triangle values, so if you get the cosine of that, cosine is adjacent, which is 4, adjacent side, over hypotenuse. So we have 4/5 of TAB equals 0. Because that should be the condition. Okay? It's not moving. So, summation of forces along y should always also equal 0. So, again, we will do the same for the y components. So, what will happen here is that if we are going to uh, uh, get first the y component of this, if we use cosine for x component, we're going to use sine. And that would be sine here, sine of that angle opposite over hypotenuse, which is 3/5. Then we have TAB. Okay? It is positive because if we project this vector on its y-axis, it's going upward. So that must be positive. Okay? And also if we resolve into its y components, this T sub BC, it's going upward. So we have positive, okay, TBC sine 45 degrees. Okay? And of course, last but not the least, we have the weight, okay? That weight produced by our particle. So that's minus because it's purely going downward. We have minus weight equals 0. So what are we really going to do here is we're just going to simply solve for TBC and T sub AB. So from our equation 1, let's label this as our equation 1. This is our equation 1. This is our equation 2. From our equation 1, we can have 4/5, okay, of TAB equals TBC cosine 45 degrees. And then if we isolate T sub AB here, okay, what are we going to get is that we have 5/4 TBC cosine 45 degrees. So you can evaluate this in decimal, okay? This is all multiplied. So 5/4 times cosine of 45. Make sure you are in degree mode. So T sub AB should be equal to 0.8839 T sub BC. So T sub AB is simply equal to 0.8839 of T sub BC. So what are we going to do is we're going to substitute this to our second equation so that we can solve for TBC, T sub BC. So if we're going to substitute that, so we have 3/5. Here's our second equation. TAB is 0.8839 T sub BC, okay, plus T sub BC sine 45 degrees. Okay? And then if we are going to uh, transpose W on the right side, okay, we have our weight. By the way, the weight, okay, the weight here can be computed by mg, simply mg. So we have 60, that's the mass of our cylinder, multiplied by 9.81, and that would be 588.6. 588.6 newtons. So we have 588.6 newtons. Okay. So furthermore, we can distribute 3/5 here. Okay. If you multiply that, that would be 0.53034 T sub BC plus T sub BC. Okay. Then we have sine 45 degrees. We have 588.6 newtons. So we can factor out TBC, T sub BC. So we have 0.530304 plus we have sine 45 degrees equals 588.6 newtons. So we can definitely isolate T sub BC. So if we are going to isolate here, divide both sides by this function or by this equation. So we have 588.6 Newton all over 0.53034 plus sine 45. You can also do shift solve or other way of getting the simultaneous equations. So if we are going to solve, that should be 475.66 newtons. That is the value for our T sub BC. Okay? Our T sub BC. And then, of course, if we are going to get T sub AB, tension at AB, we simply use this formula, 0.8839, okay, of T sub BC. So, 475.66 newtons. So, the value of T sub AB should be 420.43 newtons. And that is our answer. That is our two answer for this problem. Okay, let's continue. So for number 2 problem, let me just read this. The 200 kilogram crate is suspended using the ropes A, B, and AC. Each rope can withstand the maximum force of 10 kilonewton before it breaks. So the maximum force that is allowable in this tension AB and cables AC is 10 kilonewtons. So meaning if it exceeds 10 kilonewton, the ropes will break. Okay? If AB always remain horizontal, okay, along positive x-axis, assuming that we have that same convention with our Cartesian coordinate plane, determine the smallest angle theta to which the crate can be suspended before one of the ropes breaks. So we are going to get the maximum, or I mean the smallest angle, okay, theta, to which the crate can be suspended before one of the rope breaks. So what is the smallest angle, okay, theta here that we can allow, okay, in order for this breaks or this ropes not to break. Okay? So first, what are we going to do is again FBD, free body diagram. Draw the free body diagram. So we have this free body diagram. So it's very simple. So we have the weight. Again, free body diagram. We have a center on A. And then we have a tension. Okay. A force. Let's say force of B. Let's say I would write it force B. F sub B on the right side. Let me just rewrite. Okay. Let me just rewrite. I'm not really good in drawing even straight lines, so please forgive me for that. F sub B, and then we have weight, okay? And we have a tension right here, okay? Let's label that as F sub C, okay? Then we have an angle theta, okay? Here is our angle theta. Okay? That is our angle theta. And this angle is the same as this angle. Okay? Okay, so we're going to write again the summation of forces along x and along y. Okay, and that should equal to 0. So upon writing the summation of forces along x and along y, we can compute for the smallest angle theta. So first, along x, we have f sub b going to the right. Okay? And we have, if we're going to resolve this f sub c, it's going left. So that must be minus f sub c cosine theta, okay, equals 0. And then we have summation of forces along y should be equal to 0. Summation of forces along y. First, we have f sub c. If we're going to resolve it on our y-axis, it should be positive because it's going upward. So we have f sub c sine theta minus the weight, which is going downward. Okay? And let's first compute again for the weight. So the weight of this crate is, we have 200 kilogram times 9.81 meter per second squared. So the weight would be 1962. 1962 newtons. Okay? Newtons. So, how do we find the angle? So, of course, from our first equation and second equation, we can solve for the angle. Okay? We don't know the tensions. Okay? But we can use this 10 kilonewtons. So, first, how do we get the theta? Okay? So, if we are going to observe from our first equation, okay? From our first equation, we can rewrite this as this in terms of f sub c. Okay, that would be f sub b over cosine theta. So a quick observation for our equation 1, if we express that in terms of f sub c is equal to fb over cosine theta. Okay, this theta, okay, is not greater than 90. It's an acute angle. Okay, so what is the smallest? We are going to get the smallest. So that theta from this is always less than 90. So, and if we evaluate the theta, okay, that is less than 90, it is always less than 1. Okay? So, it can be 0.8, 0.5, 0.9, 0.7. And if we have a force F sub B divided by 0.7, 0.5, depending what angle of its acute angle of theta, okay, the F sub C would be greater. Okay? Because cosine theta would always be less than 1. So if we divide any number less than 1, let's say 1 divided by 0.5, okay? So it will be 2, if I'm not mistaken. Okay? In other words, F sub C is always greater than FP. So, we can assume that, okay, that FB, F sub C will reach first the maximum force of 10 kilonewtons before FB. So, what are we going to do with this is we're going to let F sub C the maximum force 10 kilonewton. Okay? 10 kilonewton. Since this F sub C is greater than F sub B, if the maximum force on the F sub C is 10 kilonewtons, then definitely the force in FB is not yet exceeding 10 kilonewtons because of this relationship. So, moving on, if we're going to go on our second equation, for our second equation, so we have F sub C sine theta, okay, equals the W, which is 1962. We transpose the W on the right side, becomes positive. So that if we're going to we're going to isolate theta here. So we have sine theta 1962 newtons over F sub C, which is we assume to be 10 kilonewtons. So we can solve for the theta, okay? The theta, which is the arc sine of 1962 newtons all over 10 kilonewtons. This is 10,000. Okay, kilonewtons. Don't forget the kilo. Okay? So if we're going to solve that, that would be 11.31 degrees. That is the maximum or the smallest, the smallest angle theta to which the crate can be suspended before one of the ropes break. And let's go now to our last example. Oops. Let me just bring this bigger so that you can see. Okay. So determine the maximum weight of the flower pot that can be supported without exceeding a cable tension of 50 pounds in either cable AB, or AC. Again, the very first thing we're going to do here is again to create a free body diagram. Okay, free body diagram. Then first, at this very center A, okay, so our point of reference is A. So we have the weight of the flower pot going downward. Then we have a tension, okay, T sub AC with an angle with the vertical of 30 degrees. And then we have another one, the tension, okay, tension, uh, what is this? AC or AB, A sub B. I'm so sorry. So it has given a sides of triangle 4, 3, 5. Okay, same same process. So we get the summation of forces along X. Okay, summation of forces along X should equal to 0. So first, I want this angle, okay? I want this angle 30 degrees with reference to the positive x-axis. So this should be 60 degrees. Okay? So that's my definition of theta. Okay? That is my convention. So, we have T sub AC cosine 60 degrees. It's going to the right, so it's positive. And we have minus, because if we are going to project T sub AB on x-axis, it's going to the left, so it should be minus. So cosine, again, the cos of the theta is here. Okay, cosine is 3 over 5 TAB. That's the cosine. Are there any forces left? Okay, none in the x-axis. So, in summation of f sub y equals 0 on the y-axis, so that should be TAC, T sub AC sine 60 degrees. Then, if we project T sub AB on its y-axis, that's going upward. So that is 4 over 5. So that's sine. So, opposite 4 over hypotenuse. So we have 4/5 of TAB. Okay? Minus W, the weight equals 0. So we are going to determine the maximum weight. It's W that we are going to solve. Now, if we are going to note, okay, this is our equation 1 again. Equation 1 and equation 2. Okay? If we are going to note, based from the first equation, okay, based from the first equation given, T sub AB is less than T sub AC. So before T sub AB reaches the limit of 50 pounds, the T sub AC is already in limit, which is the 50 pounds. So let's solve for the T sub AB. Okay, by setting T sub AC as 50 pounds. So if you're going to solve that, T sub AB, okay, that is T sub AC sine or cosine 60, So cosine 60 degrees all over 3 over 5. Okay? Substituting T sub AC again as 50 pounds because from the relationship, okay, before T sub AB reaches 50 pounds, T sub AC is already in the maximum because of their relationship. That T sub AB is always less than T sub AC. So we have 50 pounds, okay, cosine of 60 degrees all over 3/5. So our T sub AB would now be 41.67 pounds, which is T sub AB is, again, less than T sub AC. Okay? Before it reaches 50 pounds, T sub AC is already in 50 pounds. Okay. So, again, we're going to solve for the weight. Okay, it's very simple. So from our second equation, if I'm going to transpose this on the right side, it would be W, and then we have TAC sine 60 degrees plus 4 over 5 TAB. Then we have TAC again. T sub AC is 50 pounds. 50 pounds sine of 60 degrees plus 4/5 of TAB, which is 41.67 pounds. And our answer for our weight should be 76.6 pounds. So, that is the maximum weight of the flower pot that can be supported without exceeding a cable tension of 50 pounds in both cables or either of the cables AB or AC. And that's it for today. Thank you so much for listening. If you are new to my channel, please don't forget to subscribe and share and like or comment down below your thoughts if you learn from this subject, or if you have any queries, just comment down below. So thank you so much again. This is Engineer UJ Abat, and welcome to my channel, and thank you so much for listening, and God bless.